Good evening, everyone. Welcome to today's problem solving section, course Digital Design with Verilog, week 7. So, in today's class, we will continue with the combinational circuit design and the Verilog implementation. So, to start with, first we will start with half adder. So, the truth table of the half adder is we have two inputs. The half adder performs the addition of a two 1-bit number, like x is of 1 bit, y is 1 bit, and gives output sum and one carry. So 2 bits, we have 4 combinations, and 0 plus 0, sum 0, carry 0, 0 plus 1, carry 0, sum 1, again 1 plus 0, carry 0, sum 1, 1 plus 1, carry 1, and sum 0. So the expression S is equal to x y bar plus x bar y, and carry is x y. So the circuit diagram x and y are the input, sum and carry are the output. So this is the simplified expression because S can be written as x XOR y, which is nothing but x y bar plus x bar y, and carry is x and y. So this is with respect to the half adder. Now, what is full adder? If we have a carry input, that is again an 1-bit number, so we have a full adder. So full adder takes 3 inputs, each 1 bit. So x is 1 bit, y is 1 bit, and Cn is the input carry, which is again 1 bit, and output is sum and C of carry. Why 2 bits are sufficient? If we add like 1 plus 1 plus 1, which is nothing but 3, can be represented as 1 1. So full adder output is also 3 bit. Now, what is the truth table for the full adder? We have 3 bits, so total 8 combinations, 0 to 7. So 0 plus 0 plus 0 is 0, and this is decimal 1, decimal 1, decimal 2, decimal 1, decimal 2, 2, and this is 3. So now what is the expression? So to obtain the expression, we can use the K-map for simplification. So it's a 3-variable K-map. And the sum expression, so there is no group. So sum is x bar y bar z plus x bar y z bar plus x y bar z bar plus x y z. And for the carry, this forms a group, again this and this. So we get carry is equal to xy plus xz plus yz. Okay, so with this, for full adder, like here, if you see, we need a full adder. At the starting, we don't have any carry in, so directly we can have and half adder, but here we need a full adder to add the input carry. So this is the expression of the sum, which is x bar y bar z plus x bar y z bar plus x y bar z bar x y z. This we have already seen, and the carry expression is xy plus xz plus y z. So till here we have seen. Now let's optimize the. Okay. So if we want to optimize it, okay. Okay. So ladder area of the nest. So now can we use a half adder to design a full adder that we will be seeing? So we saw that sum is nothing but x bar y bar z plus x bar y z bar plus x y bar z bar plus x y z. In this, if we take the z comma z bar, we will obtain which is nothing but xor, and this is xor. So this is z bar xor, and this is x naught. So this is equivalent to x XOR y XOR z. And in the carry expression, the KMAP that we obtain, we had one. So to form the group, in the Z comma, so the carry is obtained from xy plus z, and here we obtain the x exclusive of y. We have to perform AND with z, and that we have to perform an OR. This. Okay, so this is the carry expression, and if you and the sum is x XOR y, and this is z. So if you observe, this is one half adder, and this is the another half adder, and we need one OR gate. So next, triple carry adder. So what is the if Maybe I'll add one more slide. Yeah. So if you want to perform a 4-bit binary addition, we consider A is a 4-bit number and B is another 4-bit number. So if we use if we have an input carry C0, we need a full adder here. This is the full adder and giving the sum S0 and carry C1. Again, we need a full adder to get sum 1 and carry C2. And we need this, we use sum and S3. With this, we have carry C4. So this is also known as ripple carry adder. And for this, now we observe we need 4 full adder. If there is no input carry, then 3 full adder and 1 half adder. So if we have say C0 is the input carry, and we need the first full adder to perform A0 plus B0, giving the input S0 and carry C1. Apply to the next full adder with the inputs A1, B1, and C1 is the carry, giving the output S1 and C2. Which is applied to the next full adder to give A2, B2, and S2 carry is C3, which is applied to the next full adder A3, B3 with S3, C4. So the time required for the addition is like now we need to, for this one, this is one path and this is the other path. If you assume that each gate has 1 unit of delay because each 2 input gates, so we have 3 gate delay for one full adder, and this full adder has to wait for this carry. So this will be the path. Okay. So for the full adder, if we consider each as 1 gate delay, that means 3 nanosecond delay, then we need 3 nanoseconds of delay here. The time period should accommodate this 3 nanosecond. And if we have 4 gate, then 4 into 3, which is 12 say nanosecond of delay is needed for a 4-bit. And if we have an n bit, n into 3, 3n time is needed. So this takes a huge amount of time because of the rippling. This adder has to wait for this carrying. So next we will see how to reduce this using the carry lookup adder. Before that, we will write the Verilog implementation for this ripple carry adder. And for this, let's use the EDA platform. I'll just share my screen here. So we will open EDA playground. Here you can write and simulate Verilog code. So you have to log in. I think you can log in through Google also. Yeah. Google. So here we have to write the design, and here you can write the test bench. So tools, we have one for VHDL and one for Verilog free simulator. So we will choose the Verilog simulator, and now we will start writing the this. Just use this. Yes. So for uh, having the like designing the repeat array adder, we need half adder, full adder, and then we will go for the with. So first let's start with the half adder. So module half adder, and the port list S, C, X, and Y, and in this inputs are S, comma C, and output. Sorry, input is X and Y. Output is S, comma C, and we need to like if we write the gate level implementation, so we have for the sum it is X XOR Y, so output followed by input, and the carry is X and Y, so C is equal to AND of X and Y. So fine, this is the module for the half adder. Now let's write the full adder module where we will instantiate this half adder. So full adder, it is S, comma C, comma X, comma Y, comma Z, and here again inputs are X, Y, Z, and the output ports are S and C, and we need the output of the first full adder, second full adder, and we have one middle. So we need some three intermediate wires, and let's call half adder HA1, which is this one, X, Y, and next half adder HA1, HA2. So this is the gate instantiation name, and output is sum directly. We get another output carry is D2. We have to apply S1 and Z. Now we have to generate the carry signal, which is from OR gate name, and the carry is generated from D2, comma D1. It is and module. So now we have to instantiate this full adder to for writing the code for the 4-bit ripple carry adder. So 4-bit adder, and the port list is sum, comma C4, comma A, B, C, 0. So the input ports are, it's a 4-bit number. So we have seen to define 4-bit is 3, down to 0. So total 4 bits A and B. And input C0 and output again 3 down to 0. S output C4, and we have 3 intermediate carries, so we can store them in wire, like assigned to the wire. And we now need to instantiate the full adder. So first full adder, and the name say F0, FA0, and output sum of 0, comma C1. Let me take everything in small. A, B, A, D. C1, A of 0, B of 0, and C 0. And we need like this 4 full adders. So I just copy this. And this is F1, F2, F3. So sum 1, sum 2, sum 3, C2, C3, C4, A1, A2, A3, B1, B2, B3, and C1 will come here. So it is replaced C2 and C3. They are instantiated it. Now in the module. Let's see the code. So any doubts in this area? Okay, so now we will write the test bench. So test bench we will write here, and module safety test bench, and no need of port list, and input in the module will be a register in the test bench. So A comma B, register CM, and output in the module will be wire in the test bench. So now we have to instantiate the 4-bit adder. So the name, let's do design and the test, and the port list we have to pass S, that is sum, comma C4, which is C out, output from the input, and the inputs are 8, comma B, comma C. So either you can follow the Alright, this is one way of writing. Or the other way of writing is dot s and then pass them. This is what C4 dot and then brackets dot A dot B dot C0. Okay, we have instantiated the model. So these are the two methods of instantiation. Next, we need to define some signals. Okay, instead of defining it, I define this one. We have to define the signal for clock and reset. So now we will initialize this. So this will be executed only once. Initial begin, and we want the clock to be 0 at the starting, and reset is equal to 1. After a delay of 20 units of time, we want reset to be 0 and end. So now we will define the clock. So always with the delay of 10 units of time, clock is equal to the complement of the clock. Now clock is also defined. Let's define a variable which is again 4 bit, say I. Now in the clock and the reset. So always at edge of clock, that is positive edge of the clock, or the positive edge of the reset. You have to do the following steps. That is, if the reset is in 1 positive, that means we will reset I to 0, and else begin we should have some values for A. This is a random number generator. The system task is $random, and percentage 16. To take a reminder of a number by 16, we can give the output 0 to 15 because we have 4 bits, so the range is 0 to 15. And similarly, B $random between 16, and carry CN is a 1-bit number, so you want between 0 and 1, so percentage reminder of 18. And with a delay of 20, we will increment I equal to I plus 1. And we will just display for 10 values, so I equal to 10. We will finish. Now to monitor the output, $monitor percentage B A is equal to percentage B is equal to percentage B C equals percentage will from percentage will be of count is equal to percentage will be what do we have to display time A B C N sum and C count. Carry on. So end and order. Okay, so control S you can save it. Now we will run. So yes, we observe with a delay of 10, how much we get? 20, with a delay of 20 units and 10 such values. But why sum is Z and carry is Z? So something is not initialized. Here we use this type of instantiation. It's somewhere A, B, and C in okay, values are generated properly, but the sum and carry are initialized. Any errors in this code? Also call half adder or say full adder D1 and let's just directly pass the value. Say it's already considered that as CC, comma, C1, comma 1, comma 1, semicolon. And let's define this as wire SS, comma CC. And this monitor, I'll just copy so that I can it's SS, CC. I think so not needed. SS, CC. Okay, maybe we will see this at the end, but yes, this is how we have to code it. Not sure something else. This is what is uh, this EDF playground does not support some of the syntax, which is actually valid. Not valid. Yes, even full adder, the values are not getting passed. Yes. Okay. So some issue like it's not getting instantiated. We will run and see at the end. Okay. So what if we have an half header and then this is the distance for half header? So we observe that if A and B are 1 1, sum is maybe 1 plus 1, right? 1 plus 1, sum 0 carry 1. Carry is x and 1, but still carries 2. Yeah, sum 0 carry 1. Okay, so now let's step. Like we will proceed with the total here. Any doubts?
I was trying at my end, and I wanted to get EP wave. So how do you add that to
Uh,
generate the?
Waveforms you are asking?
Yep.
That we use something called dollar $dump VCD file or something.
Yeah, what is the exact command I was looking?
Uh,
Maybe
exact command currently I'm not remembering, but yes,
would you know, or it's fine. Otherwise, I'll look at it.
yeah, I have used it once. Some VCD dump is there. Yeah, maybe in the end I will show.
Mm-hmm. Okay. And one more thing, I was confused with the variables. So if we use, let's say, a variable s for sum, and in one module, so would it affect another module if we use the same variable?
No, 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 no. It will not affect.
So, like for half adder, I use the sum as s, and again for full adder, I use again the variable s for representing a sum. So, would it affect the output? Because I'm getting somewhat half correct, half incorrect output. So,
No, here you if you have used S, here also you can use S. It is not a problem. Only when instantiating here, we should instantiate it properly. Like follow either the order or if you want to follow the naming, then pass by name correctly. One module here,
Can you repeat? I missed you.
like here having s, here also I can keep output 3 down to 0 as s. This will not affect. I can use x and y here.
Mm-hmm.
Again, here also I can use x and y. This will not have any effect. But if I am calling this half adder here, I should either pass whatever variable I want for sum in the same order. So I want this s to be p0, then
Right.
it should follow in the same order. Or I can follow with respect to the name dot
Mm-hmm.
s whatever variable I want in the.
Okay.
Yes. Any other doubts? So now we will see the carry lookalike header. So we said that like the delay is more because of the carry propagation. So for that we will be like generating the carry using the like we will have can we the main idea of the carry lookalike adder is that can we generate the carry before like without waiting. So our aim is like can we have C0 which is the input carry, and can I have C1 without the term of C0, like um, like C0 is anyway fine, but C2 without the term of C1. So here if you observe, when x is equal to 1, y is equal to 1, C in carry in can be 0 or 1, C out is going to be 1. So this is going to generate the carry anyway. So this we will call carry generator. And the propagate is like if x and y are going to be 0 1 or 1 0, this is going to be 1. So this is the propagate. So this is propagate. This is the carry generate. So the propagate is ai XOR bi, and the generate is ai bi. So the next stage carry uh, plus 1. So depends on the gi plus ei ci, which is the previous state carry. Second. So So C2 can be written G1 plus P1 C1, which is G1 plus P1 G0 plus, because C0 is anyway the input carry. But now C2 we have with respect to input carry. And again C3 also we will have with respect to the input carry. This nothing but G3 plus G1 plus. Okay, so now we have both the propagate and this generate. So with this, we have seen like this is generated from a header which gives propagate XOR and this generate statement. So now we need a circuit like this is the next stage carry generated without depending on the previous stage carry. Now if you see, if you have say 4 input AND gate, it can be implemented using n-1 gate. So we need 3 gates. If you have an n input gate, we need n-1 2 input gate. So 3 uh, if you like if we consider the ripple carry adder, okay, let's, so the 4-bit adder we have this is the half adder which gives the propagate and the generate statement, and the carry lookalike generator this block, and we need the XOR to generate the uh, sum. So now we have a delay of 4 whatever be the inputs, because this stage we have 1 unit delay, and this stage use 1 unit of delay. This stage use 2 unit of delay if we observe here, because this is the level 1, level 2. So 2 unit of delay. So total 4 unit of delay. Now it's Verilog code implementation. So again we implement the half adder, and this is the carry generate. So the expression for C0 to C4, and the carry lookalike adder where we have half adder, then we generate, and then we have XOR gate to the final output. And similarly for the test bench, we instantiate the module and we define the clock and reset, and we initialize it and we generate the clock, and this means the value is from 0 to 15. This will generate value 0 to 1 because it's a reminder, and this is for dollar monitor, and for the various 10 different values we observe the sum and carry. So again in this code, if you have any doubts you can ask. Why to use else statement? This is to reset. Resetting the means we are resetting the value of I to 0, and this is the actual part. So I is 0 initially, because reset is 1. That means I is 0. We start from 0, and then for after that, it will be coming else begin end. After the reset is set to 0, that it will come out of this if block, it will come to the else block, and 10 times it will give the different random values, and these values will be applied to this CLA adder, and we will have different in combinations of input and the output. Is it clear? Okay, so if no doubts, we will go to the next topic. Area overhead for the carry lookup adder. So for the ripple carry adder, um, this is a ripple carry adder. The overhead we saw was 3 times the gate delay. So yeah, that's just the, so the 2 input gate, if we see, say we consider as this 2 input, we all consider like all the gates to be 2 input gate, and for every full adder, we need 5 gate. That means for 32 bit, we need 5 into 32, which is 160 gate, and 3 into 32, if we consider each has 3 unit of delay, because it's a 1 XOR, then that this path XOR and then OR, so 3 unit of delay. That means we get 96 unit of delay for 32 bit addition. But whereas if we are using this carry lookup adder, the like here we have 2 input gate, here we have 3, and here we have 4. So if you see the gate in the carry generator itself, 31 times 1, 31 input gate, and 230 input gate, 29 3 input gate, till 131 input gate. So it is almost like this, and we need this or 1 in 2 input, 3 input, and similarly 31. So it's this itself is. So we observe that like almost there are so much increase in the area overhead for this carry look ahead adder. This gate and this gate we have seen. So to reduce it, we can have like consider a 4-bit carry look ahead adder and then design it like a ripple carry adder. So say 0 to uh, CN2, that is like 0 3-bit, again some 3-bit here, and in this way. So this way we can like reduce the gate count. Say per one it will be 6 gate plus 12, which is 28 gates almost, and we need like say 8 stages for 32-bit. So the gate count is reduced. So this we can observe in this comparison table. Yeah, when we have combining it, okay, these calculations are considering 4-bit CLA to form 32-bit adder. So we have like the gate count is almost 66,500 to input gate for a CLA, but we get improvement in time in the time. Instead of 96 units, it's just 4 units. But if we have a smaller CLA and then form a ripple carry adder out of it, we have increased the gate count, but it's still much lower with a good improvement in the delay. So other types of adders include ripple carry adder, carry look ahead adder, etc. So till now we have seen is the full adder and its optimization, that is using 2 half adders to design a full adder and a 4-bit triple carry adder. So now how can we, this is say it performs only addition. So we can say it's an unsigned addition. So when we are performing unsigned addition, what is overflow? It is like we have an A which is n bit, we have a B which is an n bit, and the output 1 carry and the sum. So this is the carry out, and this is n bit. So we get the output n plus 1 bit, 1 bit. So for example, if we add 10 plus 9, which is 19, we get a carry 0, 1. So this is the carry out. But this is not the same with the signed numbers. So when we say signed numbers, we have n minus 1 bit and 1 bit for sign. And how do we take two's complement, that is by taking the one's complement plus 1. So if we have say a minus b, this one we want to do like a plus two's complement of b. So for that, if we have like say this 1010, the one's complement is 0101. For taking the two's complement, we add 1, so it gives 0110, which is nothing but minus 10. So for that, we can use a XOR gate because A XOR B is so here whenever a bit is 1, we observe it is complemented, and we need complement only for, so we got A complement. And if we have a say one sign bit and n minus 1 the bits, so the range of two's complement is 2 to the power n minus 1 less than equal to x less than equal to 2 to the power n minus 1 minus 1. Okay, so we have this one. To understand the overflow, we will consider a few examples. Let's take plus 5 plus 12, which will be plus 17, and minus 5 minus 12, which will be minus 17. So if we write this 0, so what will be the carry here and what will be the carry here? Similarly, what will be the carry from here? Carry from here. So with this, we'll see what is the overflow and let's help it. If we add this, we will get here we will have one carry, and this will give one carry. So we have this carry as one, and here we don't have any carry. But for this, 1, 1, 1, 1, the carry is 0, and this carry is 0. No, sorry, not 0. This is 1 plus 1, 1. So either the carry is like 0, 1 or 1, 0. These are the two things. This is the 2's complement form of minus 17. So next, plus 5 plus 3. This should be plus 8. If you add here, we got a carry 0, and the output carry is also 0. This is giving plus 8. Minus 5 minus 3 is giving its answer is minus 8. So this is minus 5 minus 3. This is 1, 1, and the carry outside is also 1. So this is equal to minus 8. And similarly, if we do plus minus 3, carry 1, 1, 0, carry 1, 0, 1. So here also carry is 1. And the outside, this carry is one plus 1, 1. So this is plus 2. So here we got a carry because like we are performing m minus n, and we have a 2 to the power n minus 1. This is a carry out, which is going to the sign bit. And here minus 5 minus 3, which is minus 5 minus 3. So we have an expression in 2's complement form because this is n plus n. This is in 2's complement. And we have a carry out. So this is valid and we have a carry out. Whereas here it is 2 to the power n minus 1 minus n plus 2 to the power n minus 1. So again, it's in 2's complement form and we have a carry out. So when the overflow occurs, when the this combination, this carry bit and this carry bit, it's like 0, 1 or 1, 0. This is the condition when it occurs overflow. So 1, 1. And when it is 0, 0 or 1, 1, there is no overflow. So we are taking the XOR from this previous carry and this carry and performing for getting the carry out. This will not have any significance. And we are taking the B's complement. So A minus B is the 2's complement. And for 2's complement, this mode will select whether it is for subtraction or addition, and plus 1 for 2's complement. Clear? I'll just again switch my screen to system. This code is visible. Okay, so this is some code which I wrote it like before. I just wanted to show for the waveform. This is some code for comparator. Yeah, and it is instantiating this comparator. Okay, so for using the to display the waveform, we should first write it in the .vcd format. So we have to create a .vcd file, and the system task is $dump file, so file name .vcd, and then to that what all variables we want. So we want $dump variables, all the variables to the of the test bench, and you should enable this one open EP wave after the run. So this will only open the waveform window, and then you can click on run. So you can see the waveforms are visible, and from here you can change the radix to binary or whatever, and get signals. So if you want any intermediate signals or the test bench signals, you can just select some from here and you can append it here. So in this way, you can view the waveform. So that this .vcd dump file and the dump waves are used to display in the waveform, and you should enable this open EP wave in the EDA playground. Is it clear? This code is not from this class. I just opened to show this syntax for $dump file and $dump variables. Clear? Yes.
Those two lines would be enough, right? The dump file and dump wires.
Yes, yes, both files, both will be enough, and this you should enable. Open if the
Yeah,
wave
yeah.
option. If the waveforms are not displayed, you can just fetch it from here. Uh, yeah, from here, get signals and test bench, and from here you can fetch it.
Okay.
If it is by chance not displaying the variables, this two lines should be sufficient.
Okay. Yeah. Thank you.
Yes. So in this way, we can perform the signed bit addition and like subtraction a plus b, a minus b. So the next decimal adder, decimal numbers means 0 to 9. Um, say we have a which is 4 bit and b which is 4 bit, c in which is a carry. So can be to 9 to 0 to 9, and carry can be 0 or 1. With this, we will have the combination for sum carry out. After this, all the bits from this till 15, this will be don't care. So in the BCD addition, till this it is valid BCD numbers, the sum. From here, the value exceeds the BCD, like uh, this is valid, but this is not valid. So for that, we should perform like from 0 to 9, it is valid. From here, 10 to 19. Why 19? Some 9 plus, like in the decimal, we have 10 plus 10, which is allowed, which is like almost 20, and so we can say 0 to 19. So somewhere till 19, if we get at the output, we have to perform the correction, BCD correction, to make it a valid BCD digit. For that, we will add with 6. 6 is nothing but 1001. Wait, not a 1001. It's a 0110 binary equivalent. So for this, either this bit should be 1. So first we start with K. K should be 1, or this bit completely, if we take, we have some more combination. So if this bit is 1 and this bit is 1, that is Z8 and Z4 should be 1, or Z8 and Z2 should be 1. So we have covered all. Then only we should perform plus 6. Okay, so for this BCD correction, we will have adder. Now we have to check that whether like K plus Z8 Z4 plus Z8 Z2. If this is 1, then we have to perform 0 1 1 addition, that is 6. It is adding with 6 with this result to obtain the BCD number. Okay, so this is the BCD adder circuit. To write the Verilog code for this, we have to instantiate 2 times the 4-bit adder, one for performing the actual sum and the other for correction, and then we have to generate this carry, like output carry from this sum of S3 and sum of S2, or S3 and S1, or it is carry out. Okay, so we obtain this as the is said. Then we have to initialize this value, which is B, which is nothing but this operation is the concatenation operation. So it will merge the 0 is Z, 0 Z, 0. So we get this is Z and Z. So we get this bit applied to one of the input. The other input is this one, which is stored here in this sum. So this sum has to be passed and this B to obtain the output. Okay. So this is the test bench where again we call this BCD adder and then initializing the reset and clock and then generating the clock. So here we have a 4-bit I and it's a decimal, so percentage 10 and 0 and 1 for carry, and it will generate 10 such values with a delay of 20 units of time, and we are displaying the values. So I hope the test bench is clear as well as the code. So the next is the binary multiplier. The binary multiplier, it's like we multiply this, then this. So we need an AND gate and this and this. So for 2-bit number and multiplying with another 2-bit number, the output is 4-bit. So if you multiply an m-bit number with an n-bit, you will get n plus n bits at the output. Say if you have a j-bit into k-bit, so for this, if you observe, this is half adder will be sufficient, but here this carry has to be propagated, so we need a full adder. So for that is, we can say j minus 1 into k adders, and how many AND gate? J and E. For every multiplication, we need an AND gate. So this is. So the binary multiplier, if we have say 4 bits, B3, B2, B1, B0, A0, A1, A2, A, uh, yeah, A0, A1, A2, A3 is not there. So here it is 3 into 3-bit number into a 4-bit number. So the final output should be 7 bits. Okay. So we observe from C0 to C6, 7 bits. So how we will be performing it? It will be A0, B0, A0, B1, A0, B2, A0, B3, A1, B0, A1, B1, and A1, yeah, A1, B1, A1, B2, A1, B3, A2, B0, A2, B1, A2, B2, and A2, B3. So this is C0, C1, C2, C3, C4, and C6. So this is 4-bit, 1, 2, 3, 4-bit, and this is a carry output. Okay. So here, if you see, I think I mentioned this will come anyway directly. Here, for this and half adder is sufficient, but this carry goes. If we have another digit here, then we need a full adder. So for this here, this will come directly. Here we need a half adder. I think I changed the color. Yeah. So here we need a half adder. This carry will come here. We need a full adder and carry with this full adder. This carry and this term will be a full adder. Next, we will take this and this sum. Apply this and this sum. Okay. So this can be implemented as we have said that like for every term we need an AND gate. So 3 into 4. So 4, 4, 4, 3 times. And every like A naught, B naught we have obtained. Now this will be direct. And this we need like here one stage of ladder and this two. This is another stage of ladder. So with this we can perform the binary multiplication. So the code so this is the all the partial products we can say, and we instantiate the first carry lookup adder, and that is these results are added with the next this last row partial terms partial product. And the test bench again we instantiate the module clock, initialize the clock, generate the clock, and here this A is a 3-bit value, so 0 to 7. That's a percentage 8. Again, this is 0 to 15. So, and we are generating 10 such values with a delay of 20, and then we will, when I reaches 10, we will give $finish. So, other types of multiplier include values tree multiplier and put multiplier. Okay, so any doubts still here? Yes, option C. It consists of 31 full adder and one half adder because there is no input carry. Next question, consider a carry lookup adder for adding two n-bit integers built using gates of pan-in at most two, so two input gates. The time to perform addition using the adder is, so it's a time complexity. Because if we have an say if I have an OR gate with two inputs, like this is allowed gate. Now if we want to design an 8 input OR gate, so here we need 4 gates, so we have covered all the 8 inputs. The next stage we need 2 OR gate, and the third stage we need another OR gate. So this way we need 4, 5, 6, 7 OR gates with 3 stage 3 levels. That means we have 3 gate delay. That means how can you say it is log 2 8 is 3. So it's a weak log. This like, will be with respect to the other, the and get so 2 times of log to log n plus some constant, so it's big O, so it will be directly log n. Yes, option B. Next, an 8-bit ripple carry adder is constructed using 8 full adder. The carry propagation delay of each full adder is 12 nanosecond. The sum delay for each full adder is 15. The worst case delay of this ripple carry adder is. So the carry propagation delay for the till the 8th full adder is 12 into 7, which is 84 nanosecond, and the last full adder takes like 15 nanoseconds to get some. So the total delay is 84 plus 15, 99 nanosecond. Here, next, how many two input NAND gates are required to implement a full adder? Actually, it is 9 NAND gate. We need 8 NAND gate for calculating sum and 1 NAND gate for carry. So just draw the circuit. A and B are the inputs, and C is the implementation of a full adder using just the NAND gates. So again, the same. It's like similar to half adder. Same circuit. This is the input, and we need Cn. This will be the input to this. This will be the. This gives sum for carry. This and this. And this one. So what will be another input for the NAND gate? Generate. This should give carry. I think I made some mistake here. This is the sum. Next to generate carry. So we have 9 gates. 4 plus 4 for sum and 1 gate for carry. Yes, middle one. Okay, next question. The 8-bit 2's complement representation of an integer is, what is the decimal equivalent? So it's a 4 1 followed by 0 1 1 0, and 1's complement is this plus 1, so 0 0 1 is this minus 10. Okay, next question. Consider the following statement and on overflow happens into its complement addition. So both operands are negative and the sum is negative is called overflow. This is false. Both operands are positive and the sum is negative is called overflow. This is true. Because both operands are positive, the sum should be positive. So that's why that is called overflow. Both operands are negative and the sum is positive. It's also an overflow. So this is false. So both operands are negative and the sum is positive is called overflow, as well as when both the operands are positive and the sum is negative. Like it should be, if it is giving the opposite one. So it's like, yeah, S1 is false, S2 is true, S3 is false. Okay, going to the next question. The number of full adder and half adder required to add two decimal digits in a BCD adder is considered that there is no input carry. So for binary addition, we need 3 full adder plus 1 half adder because no input carry. And we need to add, like for BCD, this is binary addition. Next we have BCD correction or conversion. So we need to add plus 6. So we have 0 1 1 0. So we need a full adder, 1 full adder plus 2 half adder, and a total 4 full adder plus 3 half adder. Okay. So the next question, how many AND gate and adders are required in a 4-bit multiplier? So AND gate is like for each pair of bits in a multiplier, like multiplier and multiplier, you can say n and n. We need to perform the multiplication, like AND operation. So to compute the partial products. And since both are like 4 bit, we need 4 into 4, total 16 AND gate. And next for the adders addition, so we add the first 3 partial products together. So we need 3 adder plus the fourth, fifth, and sixth partial product together. So again another 3 adder, and seventh, eighth, and ninth plus 3 more adder. So and for the rest of the bits, like for the remaining bits, again 3 more adder. So total 12 adders. First three adders, again 4, 5, and 6 3 adders, 7, 8, and 9 again adder, and again we need uh, for the remaining 3 more adders, so total 12. So we need 16 and 8 and 12 adder. Okay, next question. Calculate the overall propagation delay of a 4-bit lookup adder designed using AND or a NOT gate, and each gate is a 1 unit delay irrespective of the gate. So here we said if this is 1 unit of delay, so we get a 1 unit delay here, and here we said we have 2 unit of delay, and here we have 1 unit of delay. So total 1 plus 2 plus 1, so total 4 unit of delay. Yes. So any doubts? Can you look ahead at it? Yes. So for carry look ahead adder, C2 we have C1 term. So because of that, we have to wait till the previous adder completes its computation and gives the C1 result. We don't want that. We want to compute the C1 also before, so that this block, the second block, will not wait for the first block, so that we can overcome that issue of the delay from the ripple carrier that we had in the ripple carrier. So to pre-compute this, we know we know C0 value because it is the input carry. So every carry should be in terms of the C0. So we further compute it by substituting this C0 value. Now when we have C3, C2 plus P2 C2, C2 will be this value will be substituted here. And next C4, this value will be substituted in that. So every carry is now computed using the C0 and should not, need not wait for C1 or C2, C3 to be computed. Yes. And we have this expression because if we observe that when this x is 1 and y is 1, okay, both are 1 at this place, whatever is this z, the carry is going to be 1. So that we can take as a carry generate. So we can name that as this one, A and B. The next is carry propagate. We know that if either 1 or 0 or 1, if it is there, this is the propagate. The carry will depend on the previous carry. Like this place, either 0 or 1 or 1 or 0. It depends on this value. If it is 0, its carry is going to be 0. That is fine. But if it is 0, 1 or 1, 0, it is going to be depending on the Z, that is the carry. So we have, if it is P1 propagate value, then the carry output is going to depend on the C in carry, or if this one x into y is, which is we call generate, should be 1. So in this way we obtain the carry output expression, that is carry I plus 1 expression in terms of the previous carry. Now we don't want this previous carry, so we have an expression for C1, which is G0 plus P0 C0. For C1, C2, it is G2 plus P2 C2, C1. Now C1, if we want to compute, then we have to wait. Instead of that, we will replace this equation and compute it. So the number of gates increases because we have this. The number of inputs to the gate also increases because here we need a 4 input gate, and but we are able to pre-compute the carry. So we need a half adder block. With this half adders, we compute the propagate and the generate value, and then we have a carry look ahead adder block which generates the pre-computes this carry. Now we have the pre-computed carry. We have to calculate the sum. Okay. So is it clear? Yes. Any other doubts? Any doubts in the Verilog code or so any other doubts? So if no doubts, then we can end today's session.
Sure.
Yes. Thank you so much for joining.
Thank you.
Yeah, okay. I will end today's session. Thank you so much for joining.